Number 24. A marathon runner completes a 42.118 kilometer course in 2 hours, 30 minutes, and 12 seconds. There is an uncertainty of 25 meters in the distance traveled and an uncertainty of 1 second in the elapsed time. A. Calculate the percent uncertainty in the distance. Okay, so let's just stop there. Let's just work with letter A for right now, because there's a lot to this problem. So I'm going to write down letter A over here. So it wants us to calculate the percent uncertainty in the distance. Okay, so now remember, percent uncertainty is equal to the uncertainty in the measurement itself divided by the measurement multiplied by 100. All right, so the percent uncertainty will be equal to the uncertainty that was given. If we go back to the problem, the given uncertainty in the distance was 25. So that's the value that goes in the numerator, in 25 meters, okay, divided by the divided by the measurement of the distance, which was 42.118 kilometers. So 42.188, not 118 if that's what I said, kilometers, multiplied by 100. Okay, great. So it looks like we can just go about and calculate this. But don't do that. Why? Well, remember, in order to do this percent calculation, the units of the numerator must be consistent with the units of the denominator. Now, it doesn't matter whether they're both kilometers or whether they're both meters. It doesn't make a difference, but they both got to be the same. So what I'm going to do is I'm going to convert the kilometer value into meter. Okay, so I'm going to do that here on the side. A little star here. So what I'm going to do is I'm going to convert 42.188 kilometers into meters. Okay, so let's write down what we're given. 42.188 kilometers. The kilometers go on the bottom, meters on the top, and the relationship is that there are 1,000 meters in 1 kilometer. Great. So now let's just calculate that, right? So we can essentially move the decimal 3 places to the right. So this would be 42,000 now, 188 meters. Now, remember, you might be saying, well, wait, this has 5 significant figures and this has 4, so why does my answer have 5? Well, it's because this conversion value here, let me highlight it. This conversion value here is an exact number. It's not a measured quantity. There are 1,000 meters in 1 kilometer, period. We didn't measure it. It's a known fact. And therefore, it doesn't influence the significant figure calculations. You only take into account measured significant figures when you're calculating the significant figure total. Okay, so we found the meters. So now what we can do is we can plug that in, okay, into the percent uncertainty calculation. So let's go back. So this is equal to 25 meters. That's the uncertainty divided by the measurement now is 42,188 meters. Great, so we have consistency now. So the meters will cancel, which is appropriate because the percent is going to be unitless. And now we just do the division. So take 25 divided by 42,188, multiply it then by 100, and we get a value of 0.059%. Okay, so I only have 2 significant figures in my answer because the numerator value only had 2. Okay, so that takes care of part A because we wanted to calculate the percent uncertainty in the distance. All right, so now part B. Calculate the uncertainty in the elapsed time. Well, I think they made an error here. Why? Because calculate the uncertainty in the elapsed time. Well, they gave it to us. Look, it has an uncertainty of 1 second. Yep, done, calculated it, finished, B's over. I don't think they meant to do that. What I think they meant to say here was calculate the percent uncertainty. Okay, so let's do that. Let's calculate the percent uncertainty in the elapsed time. Okay, so again, I'm going to write the formula. Percent uncertainty is going to equal the uncertainty associated with the measurement divided by the measurement multiplied by 100. Okay, so percent uncertainty will equal the uncertainty associated with the measurement. So let's go back to the problem. And they told us that the uncertainty of the time was 1 second, right? So I boxed that. So 1 second. And that's now divided by the measured time. And okay, the measured time is this, right? 2 hours, 30 minutes, and 12 seconds. So I could write down 2 hours, 30 minutes, and 12 seconds. And then multiply that by 100. But what's the problem? Yeah, right? The problem is that here I have seconds, and in the denominator I have hours, minutes, and seconds. No bueno. So we have to have one single unit throughout. Okay, so what would be easiest is if we take the denominator value and just convert that into seconds. All right, so how do we do that? Well, we're going to be looking at this in a 3-step process. Okay, so 1, convert 2 hours into seconds. Okay, let's do that first. Well, actually, I'll just tell you the whole outline. So that's the first part. The second part would be to then calculate the 30 minutes or convert 30 minutes into seconds. And then the third part will be to add all the seconds. Okay, so that's just a little map there. Let me just erase it so I have enough space. So let's do the 2 hours. So 2 hours, I'm going to put seconds on the bottom. Oh, not seconds on the bottom. Hours on the bottom, right? 2 hours on the bottom. And could I put seconds on the top? Well, I'm not sure how many seconds there are in an hour. It's 3,600, by the way, but let's assume that's not familiar. I do know, though, how many minutes there are in an hour, right? So it's 30 minutes every 1 hour. So that cancels. Then put minutes on the bottom, seconds on the top, and we know that there are 60 seconds in 1 minute. Uh-oh, sounds like my dog may have just eaten the mailman. Oh, and now my son is going crazy too. Okay, so sorry about that. Anyway, I love when the mailman comes. I don't know about you. But now, so we're going to take 2 multiplied by 60 by 60. So now we have 7,200 seconds, right? Because the minutes canceled. Okay, so this will be now the total amount of seconds from the 2 hours. The second part now is going to be to take the 30 minutes and convert that into seconds. So let's write down 30 minutes, right? Minutes on the bottom, seconds on the top, 60 seconds in a minute, get rid of the minutes. So take 30, multiply it by 60. That should come out to 1,800 seconds. Great. Now, the third part, right, is now going to be to add these 3 together. Okay, so I'll put it as over here. The third part now is going to be to take the 7,200 seconds, add to that the 1,800 seconds, and then don't forget about the 12 seconds. All right? So we'll add all of them together. So plus 1,800. I don't even need a calculator for this, but I went to it anyway. So 9,012 seconds. Great. And actually, yeah, so that's perfect. So that's 9,012 seconds. Let me just double check my significant figures here. So 2 hours. Yeah, because we were certain that it was 2 hours. So this is good. Okay. And the 30 minutes was fine. Really, and it also tells us that the uncertainty lies in the ones place for the seconds. So we do have the correct number of significant figures here. So now what I'm going to do is I'm going to go back to my percent uncertainty calculation. And I have now 1 second divided by 9,012 seconds multiplied by 100. And now let's find what that value is. Multiply by 100. So this comes out to a value of 0.01 percent. Okay. Now only one significant figure in my answer because I only had one significant figure in the numerator. All right. So now that takes care of part B. That is the uncertainty, the percent uncertainty that is in the elapsed time. Okay, so now let's move on to part C. And by the way, if you guys are studying out of this book, this problem really piggybacks off of problem number 21. So this actually breaks it up a little better in terms of, the question is just broken up in terms of the steps that are necessary. Question 21 actually just throws it all together. So you can think if question number 21 was hard, this one should help you out a little bit. If this one was a little hard and you want a little more practice, go back to question number 21. Okay, so now letter C. So letter C, it says, what is the average speed in meters per second? Okay, so let's, let me see. Let's write down what we know, right? So we know the total. So actually, let me write down the measurements associated with their percent uncertainties, okay? So I'm going to do that here on the upper left. Okay, so for the distance, we have a value of 42,188 meters, right? Plus or minus 0.059%. As well, 0.059% of what? Well, percent of this. Okay, I'm just going to leave it though in terms of percent for now. The time, right, would be written like as 9,012 seconds plus or minus 0.01%. 0.01% of what? Well, 0.01% of the 9,012 seconds. Okay, so now what we need to do, it says in C, again, it says what is the average speed in meters per second? So what we need to do is we need to calculate meters per second. So go back to the upper left-hand corner and look, I know the meters and I know the seconds, the base numbers, right? And that's how we're going to calculate the meter per second value, by using the base numbers here, by using the measurements, okay? So all I have to do is simply, well, probably shouldn't write an equal sign, but all I need to do now here is plug in the meter value. So we have 42,188 meters, and then plug in the second value, which was 9,012 seconds, and now calculate the meters per second. Okay, so let's do that. So we have 42,188 divided by 9,012. So we get a value of approximately 4.681 meters per second. Now, again, I have four significant figures here because the value in my calculation with the least had 4. So therefore, they should match. Okay, so that's the answer for part C, 4.681 meters per second. Okay, now part D. It says, what is the uncertainty in the average speed? So, okay, so let's consider that, So let's consider that in order to calculate the uncertainty in the average speed, or let me start here. In order to calculate average speed, we had to take the meters and the seconds together, right? Now remember, there was an uncertainty associated with the meters, and there was also an uncertainty associated with the measurement of seconds. Now, if you think about it, if I now basically took those two uncertainties and put them together in a single value, right, of meters per second. Now that's a single value, it's a ratio. I haven't doubled the uncertainty, but I have two layers of uncertainty, right? I have uncertainty associated with the meter value. Then I have uncertainty associated with the second value. So we can come up with this general equation, right, for uncertainty here. So part D, let's think of this, that the total uncertainty, right, and I have to do this in terms of percent because it's not an absolute. So the total percent uncertainty should be equal to the percent uncertainty of the first measurement plus the percent uncertainty of the second measurement plus the percent uncertainty of the third, etc. Now we only have two measurements here, both the distance and the time, right? Both the meters and the seconds. So I'm only worried about the first two. But if you had a whole bunch that you were taking into account, it would just, continue on forward. So let's find, or we don't have to find, but because we already did it. So in order to find then the total percent uncertainty, I need to know the percent uncertainties of both of the two measurements. And that's actually what the prior steps had us do, right? Step A had us find the percent uncertainty associated with the distance, which if you go back to part A, right, it was calculated to be 0.059, okay? And to that percent, I'm going to add 0.01% because that's the percent uncertainty associated with part B. Okay, now to find the total, we just have to add the two together, right? So the total percent uncertainty will now be equal to just adding them both together, right? It comes out to be 0.069. Now that isn't the final total percent uncertainty, because we have to take the rules into account for addition of significant figures. So very quickly, let me do this on the right side over here. So we would be taking 0.059 and adding to that 0.01. Okay, so we would get a value, right? The decimals here, there's a 0 here, there's a 6, and that's a 9. Now basically, when you add, it's not necessarily the total number of significant figures that's important. Meaning you're not looking at this and saying 2, and this is 1, therefore my answer should only have 1. What you're doing is you're looking at it in terms of decimal positioning. So what you want to do is find, so for example, in the second number, there's no more values over here. So what you do is you can create like a little line here. Okay, that's where essentially you're going to cut the answer off at. Okay, so what this is telling us is that we're going to cut the answer off at the hundredths place, right? So you only know the hundredths place of the second value. You know up to the thousandths place for the first value, but you can't be any more certain than your most uncertain measurement. And your most uncertain measurement here is to the hundredths place. So therefore, your answer cannot be more certain than the hundredths place. Okay, so now what I need to do is I need to now round the number to the hundredths place, right? So I look at the thousandths place, it's a 9, and it rounds the 6 up. Okay, so this total percent, the total percent uncertainty becomes now, I'll just approximate it because it'll become now 0.07%. Okay, now that's the total percent uncertainty. What did they ask us though? They asked us, it said, what is the uncertainty in the average speed? Okay, well we found the percent uncertainty. So how do we now find the actual uncertainty? Okay, so it's very straightforward. Just remember the formula. Going to go up to the upper right-hand corner. So this is part D continued. So percent uncertainty is equal to the uncertainty value divided by the measurement times 100. So the percent uncertainty is 0.07. That's what we just calculated. The actual uncertainty value we're going to find, and then the measurement that we're trying to find is we're trying to find the uncertainty associated with the average speed. So what is the average speed? Well, the average speed is what we calculated in part C here. So that is the number that goes in the denominator. So 4.681, right? You can put the units in if you want, it doesn't matter. Meters per second, multiply that by 100. So now, a couple of ways to find this. I'm going to multiply out the denominator. So do 0.07 times 4.681. That comes out to a value of 0.3, right? So you can, it doesn't really matter. You technically should stop it here in terms of 1 sig fig. Yeah, we'll just stop it here. So it comes out to 0.32767, but it should only have one significant figure because of the values that we're using, right? We're doing a multiplication. So I'll stop it at 0.3, and that'll now equal the uncertainty multiplied by 100. Right, so just divide out the 100. So your uncertainty value will now be equal to 0. So move the decimal place 2 places over, 0.003. And what are the units, right? Because this is an actual measurement now of the uncertainty. The measurements are meters per second. And that would now be the final answer for part D. Okay, so that's the answer for part D. So long problem, it's very complex because there's conversions going on, there's percent uncertainties, there's uncertainties, right? There's numbers all over the place, there's conversions all over the place. But the problem kind of breaks down the steps appropriately, meaning moving from A all the way to D. So thank you guys for tuning in. All right, if this helped at all, please do subscribe. Until next time.